So in this video, we're going to have a look at a process called fractional distillation. And this is the process by which we make crude oil useful, because crude oil that we get out of the ground is actually pretty useless. It doesn't do very much. We can't use it for anything. However, the different parts of that mixture, things like petrol, diesel, kerosene, they are actually very, very useful. So we use petrol for using cars, for example. Kerosene is used in aircraft for their fuel. And so if we can separate out those different fractions, those different parts of that mixture of crude oil, then we can make some money from it, and we can use it. Now, to understand how we do this, we need to understand this process here, this idea of distillation. You've done this earlier in the course, where you get, maybe, for example, you might have ink and you evaporate it, so you heat it up, and the liquid with the lowest boiling point evaporates, and then you condense it using a condenser or a liquid condenser, or even just a water bath, an ice bath, just to condense it, lower the temperature and turn it back into liquid. And then whatever's left behind with the higher boiling point stays behind. Fractional distillation works very similar, however, it also works. There are some little tweaks to that. The idea of fractional means you do several times, so you won't just do it between two liquids and just boil one off. You will do it you'll do it to several liquids within a mixture. And how do we do that? So we use something called distillation column. This is what they look like, and what you do is you heat them up at the bottom. Now, a couple of things you'll notice: they've got these pipes coming off. Now, that's where we're collected in the different fractions. You'll also notice it's not just because of the angle, they're at different heights. Now, that becomes quite important. And the other thing is they are very tall and they're very thin. Now, the reason they're tall and thin is because I'm going to heat them down here. So the further they are away from the heat source, the colder it gets. Actually, they're supposed to be quite cold up here. And that's going to be really important, because the temperature is gradually going to get colder as you go up the column. Now, to understand why this works, we need to understand what the key property of the different groups, the different parts, or the fractions of that crude oil is. So if we have a look at these are some basic hydrocarbons. You've got ethane, which has got 2 carbons and 6 hydrogens. So it's C2H6. Pentane's a bit bigger, C5H12. So it's got 5 carbons and 12 hydrogens. And pentane will have a higher melting point and a higher boiling point than ethane, because it is bigger. And they're actually all quite similar, those ones, because when we're in the grand scheme of things, the majority of those hydrocarbons in crude oil are very, very big. We're talking 40 plus carbon atoms, so they've got very high boiling points. So as I said, the bigger the molecule, the higher the boiling point. So 40 plus has to give you sort of a boiling point of over 400 degrees. However, if it's got 8 carbon atoms, it's about 140 degrees. So as a result, we can now separate them out by their boiling point. But the thing we're separating them out for is the size of the molecule, because the smaller the molecule, the less viscous it is. So that kind of means the more liquidy it is, the more fluid it is. So it gets more fluid, it gets more less viscous as you go up, but also it becomes easier to ignite. So petrol engines work very differently to diesel engines, so you can't put petrol in a diesel engine and diesel in a petrol engine, because they work very differently, and that's because of how easy they are to ignite. Because a petrol engine, for example, uses spark plugs, but those won't work on diesel, because diesel's down here and is harder to ignite. Now, how that actually works, if we have a look at the column, you'll notice it's got little valves in, and it's got these plates at different heights, and we're heating it at the bottom. So I'm going to give you three different fractions as an example. Now, the first one is bitumen. So bitumen comes in, and these are very, very big molecules. They have very, very high boiling points, and the boiling points are too high for the heat at the bottom to actually cause it to evaporate, so it just runs off as a liquid. This is used for things like the rubber crumb on a 3G pitch, for example. Now, the other two are going to evaporate as they come into the column, because it's so hot at the bottom. However, so go through the valves and they move up. However, because it's getting colder, now actually the boiling point for, let's say, the green one has gone past, or the chemical's gone past its boiling point. So now the boiling point is actually higher than, or the temperature is actually higher, temperature is lower than the boiling point of the green hydrocarbon. So the temperature is now lower than the boiling point, which means it's going to condense, it's going to turn back into liquid. So if it turns back into liquid, it's going to fall and it's going to hit and land on this plate. Now, because it lands on the plate, it's not going to go all the way down to the bottom where the bitumen is collected. It's going to run off here at fuel oil. Now, the yellow is going to continue to rise because its boiling point is much, much lower. However, the same thing is going to happen. It's going to get so high that it actually goes past its boiling point, right? So that means it's going to condense again into a liquid and it's going to run off. Some, the very, very small molecules will come out of the top and they'll be natural gas that you use in things like your stove. But as a result, we separate them out by their boiling points. So the lower the boiling point, the higher up the column it goes because it's colder and it's going to condense higher.